grind 75 in C++, we're going to do sliding window maximum. This problem isn't part of the main 75, it's actually in the extended list, but I think it's pretty clever, so that's why I'm doing it now. You're given an array of integers where the sliding window of size k is moving from left to right along the array. You can only see k numbers in the window at a time. It moves by one position. Return the max. So if you got this input, you got a sliding window size of 3. In this first window, you got 3 as your max. In the second window, you just have that same 3 as your max. Don't highlight the whole thing. In the third window, 3 has fallen out, so now 5 is your max. And then the next window, it's still the same 5. Next window, it's the same. Actually, it becomes 6. And then the last window becomes 7. So let's compare this against sliding window median. In sliding window median, the approach uses 2 heaps, a min heap and a max heap, and each one holds half of the window in it at a time. So you can get the median in constant time as long, and then the runtime really comes into play of adding things and removing them from the window. And that takes logarithmic time due to the heap operations and maybe an extra balancing step. And that gives you a total runtime of n log n. The way that this algorithm achieves better is because the median can go up or down depending on the value of the input. And it can go up or down depending on the value of what falls out of the window. The sliding window maximum, the value can only go up. The max can only increase as you add things to the window. And it can only decrease as you remove things from the window due to expiry. And since that direction, you basically cut the number of directions an operation can affect the output by in half. And that's how you end up achieving linear runtime instead of n log n. The tricky part of this algorithm that took me a little bit longer to kind of get a handle of is how to deal with expiry, the oldest end of the sliding window. How do you know when something's going to fall out? Because if you use something like, I don't know, if you use a heap to keep track of whatever like the biggest item is, maybe you could get the biggest item. You could get similar n log n runtime, but then you run into trouble of, well, now that you're not preserving the order of things in the window, you need to recover that in order to know when they are going to fall out of the window. The other trick that's a little more straightforward, I think, is in any given window, you only need to know the biggest item in it, and you need to know when that biggest item is going to fall out. So for example, in this first window, we only care about this 3. We don't care about this 1. And we need to know when this 3 is going to fall out. In the second window, we still care about that 3. And then in the third window, we suddenly only care about this 5. We don't care about -1. We don't care about -3. We want to know when this 5 is going to fall out. So the trick is in the window, we're actually going to track the indexes instead of the values themselves. You could track the index and the value, but it's also pretty simple and I think a little more straightforward actually to just track the indexes. And then every time you need the value, you look it up in the nums array. So I'll go ahead and start writing out some skeleton code. So the return value is going to be a vector. Int ret for return. And we're going to use a double-ended queue for our window. I think that's pretty intuitive. I'm going to call it Q for Q. Double-ended queue, I think that's it. You see the term double-ended queue. or DQ in most languages. That's kind of what they call it. It's a pretty common naming convention in the standard libraries. We need to return our output, and then we're gonna need a main loop. So for int. And since we're tracking indexes in our window, but the window size may be smaller than k, because we're going to try to actually remove things that we don't care about from the window. So I'm going to use a left and a right pointer. So L equals 0, right equals 0. They're not really pointers, they're index counters. The loop itself is going to increment along R. So the rightmost side of it, R being the newest things in the queue, L being the oldest things in the queue. So if R is less than the size of nums, and increment R. Okay, we got that. What do we actually do in this loop? I'll go ahead and add kind of the simplest part. Notice that I'm starting at the end of the loop first. Notice that our output is actually a little bit smaller than the input. It's smaller by this amount. So we do need to check if, I'm adding the part where we actually put things into our output. So if R is greater than or equal to k minus 1, we want, by convention, I'm going to have both the left and right pointers be inclusive of our window. So as long as, and also the arrays are 0 indexed. So if R is, if k is 3, if R is at least 2, 0, 1, and 2, then that's our window, and then we can start putting things in our output. So vector dot push back. What are we going to push back? It's going to be something from nums. And note that we only care about when the biggest thing in our queue is going to expire. Meaning, we don't care about anything newer than it that is, sorry, we don't care about anything older than it that is smaller. We like, if this is our queue, well, we don't care about these. We can immediately remove them. We want this biggest item to be the oldest thing in our queue. That gives us the constant time retrieval, as opposed to, doing like a kind of a brute force approach would be O of n times k runtime if you were to do a linear scan through the window at every step. If the window was sorted, then you could do, say, like constant retrieval, but then you lose the ordering of when things should expire. And that becomes tricky too. And that's the same problem you have with using like a heap-based approach. So since we're gonna make the biggest thing be the leftmost item in the queue at any time. So it's gonna be nums dot the front really. So just the first item, not nums0, nums of q of 0. It could be 0. You could also do, q dot front. That might be a little more like, I don't know, 6 of one, half a dozen of the other. This is a little smaller and I think easier to understand at a glance. And then we're also going to move our left pointer at this point. Because our window is big enough, this is kind of in the beginning, we want to increase our window a bit. And yeah, I think that's it for that. So next I'll do the core part of the algorithm, which is we want to remove everything that's newer and everything that's smaller than our newest item that we're about to add. We're going to go ahead and remove them first because we're not going to care about them. If they're smaller than what we're about to add, they're never going to be the solution ever. So we can just delete them. It's fine. So while while the queue is not empty, first of all, not queued empty, and queued up back is less than or equal to. You could do less than or less than or equal to. Either will be correct, but this will keep the queue a little smaller if you have a looser removal requirement. It's fine. Int back, and we want nums of int back. Nums, the last item in our queue, since we're tracking indexes, we have to still look it up, is less than or equal to nums of what's going to be our newest item. And then q dot pop back. And then finally, we can add it. So q dot push back r. Now we've got something in our queue. What is the next step? So we've got adding things to our output and moving the left pointer. We've got removing things that will never ever be the solution because they are newer and smaller than what we're about to. They're new-ish. They're not like going from newest to oldest. We're removing things that are smaller than we're about to add. So now we need the part where we actually expire things out the end of the window, out the left side, the things that are oldest and still biggest. This is the step, the only step that could decrease our window value or our window maximum. So since we're tracking the indexes, q.front is the index of our oldest item. So if the front of the queue is less than our left pointer, q.popFront. And this pop front is why we're using the double-ended queue instead of something else. And this will only happen once per iteration, so that you could do a while loop. Really, you could do a while loop on any of these, but actually you couldn't do while for this, but this you can do while for. But I'm gonna not, because it'll only happen the once anyway. Is there anything missing? I'll parse it over. Let's talk about run time and space. And I'm gonna do the example at the end after submitting, because on this problem, the examples are kind of tedious, and that'll give people the core material, and then they can tune out or close it, unless they want to see the whole example. All right, so we've got O of n time. That was the whole point of this. How do we know it's O of n time? We've got an O of n loop, and in the loop, this is constant, this is constant, all these are constant. So how do we know that this is constant? Well, it can only happen, we're going from the right to left end of the queue. And if we don't pop something off, we're shrinking the queue and checking at the same time. So if we don't remove it, then we immediately break. And if we do remove it, well, it's removed. So we're never going to mess with checking that item on any future iterations, because things only get added to the queue once, meaning they can only be removed once. So this becomes, you could do it, up to k times in a single iteration of the loop, but you're never going to do it more than a total of n times at all, the whole time. So that means it's going to be, it's not going to increase our runtime. So that gives us the linear runtime. What about space? Well, this is an output, so we're not going to count that. We've got some integers, but this queue item, suppose the input is strictly decreasing so that we never remove things with this step. Well, we still remove things with this step, so we end up with up to k items in the queue at a time. So you have O of k space. And then we have to note, since k is a value, not a size of an input, we should note that k is less than or equal to n. So you still know that bounds it to O of n space, except k could be smaller. So it's more appropriate to say O of k space. So that's it for time and space. I'm going to go ahead and I'm going to scan this and then run it for syntax. Let's say, so we create our values, we initialize the loop. We have the step where we remove new things that are too small, and then we add them there. And then here we remove things that are too big, or sorry, we remove things that are outside the window, that are too old. Remove things too small, remove things too old. And then finally, starting from once the window's big enough, from there on out, every step we add the front of our queue and we increment the left pointer. So I think that'll do it. I'm gonna run it. Vector cannot dot operator on a type. Oh, wait, what did I do? It's not vector. Oh my gosh. Ret for return. Return is our output vector. Cool, cool. Submit. And then I'll mark it off and then I'm gonna do the example. So marked off, sliding window maximum. Yeah. So this is our solution. And let's go through it, guys. If you're still sticking around, that means you're interested. All right, we've got our input. And then k equals 3. I'm going to put the output up here. Our output is right now empty. And then we've got our queue data structure. I'll put that down here. Our queue's there, output up here. So return queue there. And we've got our left and right pointers. Okay. So we've got our maximum. I hate that. That autocomplete. I need to figure out how to turn that off. All right. I'm going to do dots for our left and right pointers. They're starting off at the beginning. Top of the loop. If left and right are, there's a 0, so the queue is empty. So we're not going to pop anything off. We're going to push back R. R is 0. That means that 0, so this, well, left is also 0, so left, the front of the queue is our candidate output. So star for the candidate. And then if queue.front, so if 0 is less than 0, it is not, so we're not going to do that. And if R0 is greater than or equal to 2 minus 1, 2, so it is not, we're not going to do that. Next iteration. The queue is now not empty, and it never will be again. Potentially, actually, no, it could be. It could be empty again. Not now. If the back of the queue, so if nums of 0, and so as a, I guess I'll do 2 stars. The back of the queue is still, it's still 0, so the front and back are the same at this point. Nums of R. R is actually here now. R is 1. Just keeping track of that. Is 3 is nums of R, so is 3 greater than or equal to the back of the queue? 1. It is, so we're going to go ahead and remove that. And we're going to add 3 onto our queue. Not 3, we're going to add 1 for the index of it. So that puts our our back of the and front of the queue are now both, them shifted over a little bit. Back in front of the queue is our window expiry. So is this less than this? It is not. So we're not going to do that. And our window is not yet big enough. R is still at 1 and not 2, so we're not going to do that. Next iteration. Loop is, or queue is not empty. Actually, the queue is I think No, never, I take it back. It's the same thing I was thinking earlier. Is the back of the queue, so is 3 less than the new item, which is -1? It is not. 3 is not less than -1, so we're not going to pop anything off the queue. And we're going to go ahead and add the index of -1, so 2 to our queue. Is the front of our queue falling out of scope? So is this to the left of this? It is not. So we're not going to do that. Now we're finally going to add something. So R is at least 2, K is 3, K minus 1 is 2, R is at least 2. So now we're going to actually add something to our return. It's going to be from the front of our queue, which is 1. It's going to be this 3 here. And then we increment our left pointer. So that moves over here. This is finally going to that. Okay. So our queue size, actually, I should have moved the star. So now we have these things. And that star, the right star should move to the right every step of the loop from here on out. Next iteration. Queue is not empty. The back of the queue, so this -1, is it less than, move the right pointer up because of the loop iteration. Is it less than -3? No, it is not. So we're not going to do that. Not going to, and so we'll add this -3, which is index of 3, to our queue. Remove these brackets. Okay. Is the front of our queue expiring? It is now because we've got 1, 2, 3. Is it? Wait. Our left pointer. No, it's not going to expire quite yet. This star. So the front is less. Front is 1. 1 is not less than 1. So that doesn't happen. If R is, yeah, this is going to be true from here on out. So we're going to add something to our output, which is the front of our queue, which is this 3 here. Is that index 1? And move our pointer to the left. Now expiry will come into play very soon. Next iteration, queue is not empty. Our new number, which is, move that right pointer to the right. We're looking at 5 now. So now 5 is greater than, first off, is greater than everything in our queue. So this -3. So we're going to remove that, which is at index 3, 0, 1, 2, 3. It's greater than that. It's greater than -1, so we're going to remove its index 2. And, you know, I'm going to put stars on things that are in the queue, I guess. So 5 has knocked out -1 and -3. Is it going to knock out this 3 as well? Well, actually, we didn't. Well, yeah, it is going to knock out the 3. 5 is going to knock out 3 because we have that extra item in our queue. We would have expired this 3 anyway, but actually the 3 is going to get removed due to this step, not this step. So 5 is going to knock out 3. And we remove it. And then we finally add it to our queue. So that is an index, I think 5, 0, 1, 2, 3, 4. It's an index 4. Alrighty, that gets knocked out. So now we only have the one thing in our queue. Okay. Now we're gonna, this is true, add something to our output, so it's gonna be 5. And then increment the left pointer. Increment the right pointer at the top of the next loop. And our new item is gonna be lucky number 3. That is not gonna be greater than 5, so we're not gonna remove anything, but we do add 3, so its index is 4. Index should be 5, actually, because I think this needs to move. 1, 2, 3, 4, 5, 6. No, it's an index 6. Wait, 1, 2, 0, 1, 2, 3, 4, 5. No, it's at 5. All right. We do the removal step, I think. So now we've got the front of our queue is index 4. That is this thing. It's not gonna fall out of scope because our left pointer hasn't gotten there yet. So now we add things to our output. We still have this 4, which is putting this 5. Okay, this needs a star next to it because it's in our queue now. This 5 is still our front leftmost thing. That's going to get added to the output. Move the left pointer over. And continue on. 0, 1, 2, 3, 4. Oh. 0, 1, 2, 3, 4. Okay. So maybe this would have expired. If it, yeah. That never triggered yet still. Or did it? Anyway. Next iteration. So we're gonna move this dot over 1 for the right pointer. And then we'll have a new item, 6. 6 is gonna be greater than this 3 here. So it's gonna knock out 3. And then we're gonna move its index from our queue. 6 is gonna knock out 5 as well. So now our queue is empty. And in this case, our queue is empty. So now we're gonna go ahead and add 1, 0, 1, 2, 3, 4, 5, index of 6. All right, fair enough. 6 to our queue. And now we're gonna check for expiry. If the front, this is, you can tell by this, and the output is strictly increasing, or it's strictly non-decreasing. This is never really gonna trigger. All right, so you've got, that's not true because there our leftmost item, this 6 is not to the left of this dot. If R, so that's always gonna be true. So we're gonna go ahead and add 6 to our output. And then move the left pointer. Finally, we're getting to the last iteration. I'll move the right pointer at the start of it. Okay, we've got a 7. We're comparing 7 to 6. It's going to knock out 6. And remove that. And then our queue is empty, so we're going to go ahead and add it. Boom. With that pushback step. This expiry step isn't going to happen because this dot is to the left of the leftmost star. And then this is always going to happen, so we add 7. The value nums of 7 is still 7 to our output. Increment the left pointer, and then exit. Okay, so we ended up with this same output that we expected, 3, 3, 5, 5, 6, 7. The tricky bit is it doesn't really, neither of these examples handle the expiry, which I'm not going to do a second example because they take so long. But that is something to worry about. You do want to test your expiry window. So you want something where you've got, a decreasing sequence of inputs where the biggest item, you want a decreasing sequence where you got things that are farther apart than k. So something like if you had an input that looks something like, let's say k equals 3, then you could do, I don't know, 6, 5, 4, 3, 2, 1. This is one where the maximum is going to start out high and it's only going to decrease from there. And it'll decrease because of things falling out of scope. That would test this part of it. Now you could throw in some extra stuff like 6, 1, or 6, let's say like that, and that, just to make sure that you do also test this part of it. So you want to say add something that's bigger. So then maybe you have a window of this, and then when you got a window of this. When you go to add the 4, you'd knock out that, and then you just have this in your window. And then 0, you'd add that. And then at the next iteration, maybe this would get expired, actually. So when you add the 0, that'll get knocked out. So then you'll just have these two things. And then 4 becomes your max. Then you add the 2, that'll knock out 0. And then this is your window. But then you add this last 0, and the 4 falls out. So then you have 2 as your maximum. This would be, I think, a better test case than what this provides. This one's actually kind of tedious, and in hindsight, I should have done something like this. But it's been a long enough video, and we already submitted, so you guys have a beautiful evening.